Night settled over the granite face long before the men stopped working. 3,000 meters above the valley floor, the mountain held its cold like iron. Snow gathered in the black creases of the rock wall, drifting slowly down through the beam of a single carbide lamp. The light flickered against steel teeth the size of wagon wheels. Then the machine began to move. A grinding roar rolled through the tunnel mouth, deep enough to be felt in the ribs before it was heard by the ears. Chains tightened. Pistons slammed forward. A ring of cutters pressed against the living stone of the Alps. 900 tons of iron leaned into the mountain. Granite did not break easily. It was older than the valleys below it, older than the forests, older than the villages scattered along the river plains. For millions of years, it had stood immovable, its walls thick enough to bury entire cities. But the machine did not slow. Steel teeth bit into the rock face, and sparks burst outward in violent orange arcs. The cutters screamed as they chewed into the granite, shaving it away grain by grain. Every second, another layer collapsed beneath the pressure. For centuries, the Alps stood like a wall thrown across the heart of Europe. Not a border drawn by kings or treaties, but a barrier shaped by the slow violence of geology. Towering ridges of granite and gneiss rose thousands of meters above the valleys below, their peaks buried beneath ice and their slopes carved by ancient glaciers. From a distance, the mountains appeared magnificent. Up close, they were something else entirely. An obstruction. Trade caravans crawling north from the Italian. Planes found their journey strangled by narrow passes that twisted through unstable rock and avalanche corridors. Wagons broke their axles on steep gradients. Horses collapsed in thin air. Entire convoys vanished when winter storms closed the passes for months at a time. The St. Gotthard, the Simplon, the Brenner, each route offered a crossing, but none offered safety. Merchants paid the price first. A shipment of silk or machinery could take weeks to inch across the mountain passes. Costs doubled, sometimes tripled, as goods were unloaded from wagons and carried by mule over steep ridgelines before being reassembled on the other side. What began as trade often ended as loss. Armies discovered the same truth. Moving men and artillery across the Alps demanded patience measured in weeks. Snow buried roads. Narrow switchbacks forced long columns to halt while a single wagon struggled upward. The mountains turned logistics into a gamble. By the middle of the 19th century, the problem had become impossible to ignore. Europe was changing. Railways had already conquered most of Europe by the time engineers began to study the Alps with serious intent. Across the plains of France and Germany, iron tracks ran through farmland and river valleys in long, straight lines. Steam locomotives hauled freight across hundreds of kilometers in a single day. Coal from northern mines fed steel furnaces in distant cities. Grain from eastern fields reached western ports before it could spoil. The continent was being rewired with steel. But the network ended abruptly at the base of the mountains. To the north, rail lines surged toward the Alpine wall before stopping, in narrow valleys where tracks could go no farther. To the south, Italian railways pushed northward with equal determination, only to halt beneath the same towering barrier. Between them stood nearly 200 kilometers of solid mountain. Merchants felt the break in the network immediately. Goods arriving by rail in the north had to be unloaded, transferred to wagons or mule caravans, and dragged over the steep passes before another train could carry them onward from the southern side. What should have been a continuous journey fractured into a slow procession across ice and stone. Every transfer cost time. Every delay cost money. By the 1850s, the imbalance was visible across Europe's trade ledgers. Industrial goods manufactured in Germany and Switzerland moved sluggishly toward Italian markets. Italian textiles and agricultural exports crawled north through the same narrow corridors. The Alps were no longer simply mountains. They had become an economic choke point. Political leaders understood the danger quickly. Control of a reliable Alpine crossing meant control over the fastest commercial route linking northern industry to southern ports. The nation that solved the mountain problem would command the arteries of continental trade. The proposal arrived not as a blueprint, but as a challenge. In the early 1860s, a small circle of European engineers began presenting a plan that many officials initially dismissed as fantasy. Instead of climbing the Alpine passes with endless, Spirals of track, they argued for something far more direct. A railway tunnel driven straight through the mountain. The distance alone seemed absurd. The granite mass beneath the central Alps stretched for kilometers in every direction, a fortress of stone formed under pressures that had folded entire continents. No railway tunnel in existence approached the length being proposed. Most tunnels of the era were measured in hundreds of meters. This one would stretch for more than 15 kilometers beneath the peaks. Even the boldest engineers hesitated. To drill such a passage using traditional methods, hand drills, black powder, and human labor would require decades. Thousands of workers would have to chip away at the rock face day and night. Progress would advance at little more than a meter per week. At that pace, the tunnel might not be finished within a generation, yet the pressure to attempt it continued to grow. Railway companies understood what such a passage would mean. A direct line beneath the Alps could shorten travel between northern Europe and Italy by hundreds of kilometers. Freight trains could run year-round, unaffected by avalanches or winter storms. Passenger travel between the industrial north and the Mediterranean would be transformed overnight. But the promise of speed and profit was not the only force pushing the idea forward. National pride had begun to attach itself to the project. Across Europe, governments were competing to demonstrate the strength of their industries and the ingenuity of their engineers. Railways had become monuments of national power, iron declarations that a country possessed the technology and wealth to reshape the landscape itself. Driving a tunnel through the Alps would become something greater than infrastructure. It would be proof that modern industry could overpower one of the continent's most formidable natural barriers. Still, the question remained painfully simple. How? Traditional mining techniques could not cut through kilometers of granite at the required pace. The rock was too hard, the distances too vast, and the ventilation problems too severe. Workers deep inside such a tunnel would suffocate long before they reached the midpoint. What the engineers proposed instead bordered on mechanical revolution. They imagined a machine large enough to attack the mountain continuously, an iron structure capable of grinding its way forward through solid rock. The machine that would challenge the Alps did not begin in the mountains. It began in fire. Across the industrial foundries of Central Europe, steelworks already thundered day and night, casting rails, locomotive frames, and bridge girders for a continent racing into the age of iron. But the machine envisioned for the Alpine tunnel demanded something far larger than any railway engine or factory press. It required a machine built to fight stone. Engineers designed its core around a rotating drilling head, a circular steel plate large enough to fill the tunnel's entire diameter. Along its face would sit dozens of hardened cutters forged from tempered steel. Each cutter was shaped to fracture granite under immense pressure, chipping away the mountain grain by grain. Behind the cutting head came the real weight of the machine. A massive steel frame would anchor the mechanism while hydraulic pistons pushed it forward into the rock. These pistons, driven by pressurized systems fed from steam-powered pumps deeper in the tunnel, would exert thousands of kilograms of force against the granite wall. The machine would not simply spin. It would press, grind, and crush. To support that pressure, the entire structure had to be enormous. Layer upon layer of reinforced iron beams formed a rigid body capable of absorbing the violent resistance of the mountain. Gear systems the size of wagon wheels transmitted rotational power to the cutter head. When fully assembled, the machine weighed nearly 900 tons. Transporting such a structure into the Alps presented its own logistical battle. Components were forged in separate factories, massive steel rings, gear assemblies, pistons, and support frames, each too heavy to move in a single piece. They were loaded onto railway flat cars and carried as far as existing tracks allowed. From there, teams of laborers hauled them into the mountain valleys using heavy wagons and temporary rail spurs. The final assembly took place at the mouth of the tunnel itself. Engineers worked beside blacksmiths and mechanics to bolt together the steel skeleton piece by piece. Rivets glowed red in portable forges before being hammered into place. Chains lifted massive components into alignment while surveyors checked measurements again and again. Precision mattered. A misalignment of even a few centimeters at the tunnel. Entrance could become a deadly error, kilometers deeper in the mountain. The first contact between steel and granite did not happen gently. When the mountain borer began its work, the cutters struck the rock face with a vibration that traveled through the entire machine. The steel frame shuddered under the resistance of stone that had not moved in millions of years. For a moment, the rotating head seemed to stall, as if the mountain itself had pushed back. Then the cutters bit deeper. The machine's design relied on a simple but brutal principle: pressure multiplied by repetition. The circular cutter head rotated slowly, its hardened steel teeth scraping and fracturing the granite surface with each pass. At the same time, a series of hydraulic pistons mounted behind the drilling head forced the entire 900-ton structure forward. The result was relentless compression. Each tooth struck the rock with enormous force, cracking microscopic fractures into the granite. As the head rotated again and again, those fractures expanded until fragments finally broke loose from the wall. What began as hairline cracks turned into shattered stone. The broken material fell beneath the rotating head where metal scoops gathered the debris and fed it onto a conveyor system. From there, crushed granite traveled backward along narrow rail carts that carried the rubble out of the tunnel mouth. The mountain was not blasted apart in dramatic explosions. It was consumed slowly. Every hour the cutter head chewed a little, farther into the rock, grinding away layers that had formed under prehistoric pressures deep beneath the Earth's crust. Dust filled the air like smoke as thousands of kilograms of stone were reduced to fragments. Progress was measured in meters. Surveyors followed behind the machine, constantly checking alignment. A tunnel driven even slightly off course could miss its target entirely when the two ends attempted to meet deep beneath the mountain. Instruments measured angles with obsessive precision, ensuring the machine remained perfectly aligned with the planned route. Ventilation became a battle of its own. As the tunnel stretched deeper into the Alps, fresh air had to be forced through, long ducts using powerful fans driven by steam engines outside the mountain. Without constant airflow, the dust from drilling could choke workers within minutes. The heat generated by friction and machinery quickly transformed the tunnel into a suffocating chamber. The deeper the tunnel cut into the Alps, the less predictable the mountain became. Near the entrance, the granite had behaved exactly as engineers expected: dense, stubborn, but stable. The cutters fractured it slowly. Debris flowed backward along the rails. The machine advanced with brutal patience. But kilometers beneath the surface, the mountain carried pressures that no survey map could fully reveal. Granite deep inside the Alps had spent millions of years compressed beneath layers of rock and shifting tectonic plates. When the machine opened a hollow space inside that immense weight, the surrounding stone did not always remain still. Sometimes it fought back. Miners called the phenomenon a rock burst. Without warning, the tunnel walls would shudder as trapped. Geological pressure suddenly released. Chunks of granite could explode outward from the surface with the force of artillery fire. Steel braces bent under the shock. Tools scattered across the ground. Men had seconds to move. Even when the stone did not burst, it crept. Surveyors began noticing that sections of tunnel already drilled weeks earlier were slowly narrowing. The immense pressure of the mountain above forced the walls inward by millimeters each day. Timber supports cracked under the strain. Steel reinforcement frames had to be installed constantly to prevent the tunnel from squeezing itself shut. Then came the heat. Far beneath the surface, the natural temperature of the rock climbed steadily. Combined with the friction generated by the cutter head and the steam-driven machinery, the air inside the tunnel thickened into an oppressive furnace. Sweat soaked through workers' clothes within minutes. Breathing became difficult as the warm air filled with dust and mineral particles. Ventilation fans struggled to keep up. Long ducts carried fresh air from outside the mountain, but the deeper the tunnel stretched, the harder it became to force oxygen to the drilling face. Inside the tunnel, time lost its meaning. Sunlight never reached the drilling chamber. The only illumination came from rows of dim lamps hung along the rock walls, their weak glow barely cutting through the haze of dust suspended in the air. Every surface, boots, tools, clothing, even the steel frame of the machine itself, was coated in a thin layer of powdered granite. The mountain borer never truly slept. Crews rotated in shifts that lasted 12 hours, sometimes longer when mechanical problems slowed the operation. As one group staggered back toward the tunnel entrance, another moved forward through the narrow passage, stepping over rails and hoses toward the grinding roar of the cutter head. The sound never faded. A deep, mechanical thunder echoed constantly through the tunnel walls as steel teeth scraped against granite. The vibration traveled through the ground beneath the workers' boots and through the iron ribs supporting the ceiling. Even when men lay down to rest in temporary bunk chambers farther back in the shaft, the tremor of the machine pulsed through the rock. Many learned to sleep with the mountain shaking around them. At the drilling face, work moved with rigid precision. Teams of mechanics monitored the cutter head, watching for teeth that had worn down from grinding stone. Replacing a single cutter required crawling into the narrow gap between the machine and the rock wall. The steel head towered overhead like a rotating saw blade large enough to tear apart a locomotive. When the machine stopped, the silence felt almost unnatural. Workers scrambled across the metal framework, carrying replacement teeth, each weighing several kilograms. Bolts were hammered loose with heavy wrenches, worn cutters pulled free, and new sharpened pieces installed before the machine could resume its relentless rotation. Every minute of delay slowed the tunnel's advance. Behind the machine, other crews handled the debris. Broken granite poured backward along metal conveyors before dropping into waiting rail carts. These carts rattled constantly along the narrow tracks, hauled by small locomotives that carried the crushed stone out of the mountain. The tunnel floor was rarely stable. Water from hidden fractures seeped across the ground, mixing with drilling dust into a slick gray paste that clung to boots. The air smelled of hot metal, damp rock, and oil from the machinery. Breathing itself became labor. Even with ventilation ducts forcing air into the tunnel, dust often thickened into clouds that burned the throat and lungs. Many workers tied cloth over their faces, though the fabric did little to stop the finest particles from entering their bodies. Coughing became a constant sound in the underground chambers. Injuries were common. Steel cables snapped under tension. Loose fragments of granite dropped from the ceiling without warning. Fingers were crushed between machinery parts. Men slipped on wet rock and vanished beneath moving rail carts. Still, the crews returned each shift. Most were miners accustomed to danger, drawn by wages higher than those offered in ordinary quarries. Others were farmers from nearby valleys whose families depended on the money earned inside the mountain. They understood the risks, but they also understood the scale of what they were building. The warning came first as a tremor. It was subtle, barely noticeable beneath the constant vibration of the drilling machine. Workers near the cutter head felt the shift through the soles of their boots before anyone could identify its cause. The granite wall ahead of the machine shuddered once, then fell still again. For a moment, the tunnel returned to its familiar rhythm, steel teeth grinding, pistons forcing the machine forward, rail carts rattling through the darkness. Then the mountain moved. A sound like distant thunder rolled through the rock ahead. Not the sharp crack of falling stone, but a deep rupture traveling through the granite itself. The tunnel walls groaned as invisible pressure released somewhere beyond the drilling face. Someone shouted. The machine operator pulled the control lever, halting the rotation of the cutter head. Hydraulic pistons froze mid-stroke as the massive steel frame settled against the rock. Dust drifted slowly through the air as the grinding roar collapsed into silence. For several seconds, nothing happened. Then the granite exploded. A violent burst of rock shattered outward from the tunnel wall with terrifying force. Fragments of stone tore through the drilling chamber like shrapnel, smashing lamps and ricocheting off the machine's steel frame. Workers dove for cover as slabs of granite slammed into the ground around them. The pressure trapped inside the mountain had finally found release. Engineers would later call it a rock burst, but inside the tunnel it felt like the mountain itself had struck back. Chunks of granite the size of barrels tore free from the ceiling. One crashed directly onto a rail cart, flattening the steel frame beneath it. Another smashed against the drilling machine's support arm, bending the heavy iron brace nearly in half. The air filled with choking dust. Men scrambled through the darkness, dragging injured workers away from the collapsing wall. Somewhere near the rear of the chamber, a lantern fell and shattered, leaving that section of the tunnel in total blackness. Then came the second sound, A cracking noise echoed overhead, sharper this time. Surveyors recognized the danger immediately. The initial rock burst had fractured the surrounding stone, and the mountain above the tunnel was beginning to shift. "Out!" someone shouted through the dust. For several days after the collapse, the tunnel remained silent. No drilling, no rail carts rattling across the tracks, no steady thunder of the machine biting into granite. Only the distant hum of ventilation fans pushed air slowly through the damaged shaft. Engineers moved cautiously through the debris field, studying the wreckage illuminated by lantern light. The collapse had buried the front of the drilling chamber beneath thousands of kilograms of shattered granite. Steel support ribs were twisted out of alignment, timber braces had splintered under the sudden shock of the rock burst. The cutter head of the machine, once the sharp iron circle meant to grind through the mountain, was now invisible beneath the rubble. For a moment, some believed the project might be finished. Extracting a 900-ton machine from a collapsed tunnel deep inside the Alps was not a simple repair. Clearing the debris alone would require weeks of labor. And even if the rock could be removed, the engineers still faced the larger problem that had caused the disaster. The mountain itself was unstable. Surveyors began mapping the fractured rock around the drilling chamber. Their instruments revealed a network of stress cracks spreading through the granite like invisible veins. The earlier rock burst had relieved only part of the pressure locked within the surrounding stone. Another collapse could happen at any moment, yet abandoning the tunnel was not an option. The final meters of granite were the most carefully measured. By the time the tunnel approached completion, two separate drilling fronts had been advancing toward each other for years, one cutting south from the northern valleys, the other grinding north from the Italian side of the Alps. Each machine followed survey lines plotted with obsessive precision, guided by instruments that attempted to map an invisible line through kilometers of solid mountain. If those calculations were wrong, even by a small margin, the two tunnels could miss each other entirely. Inside the drilling chamber, the workers understood what was at stake. The machine continued its slow advance through the granite, its cutters grinding through the last stretch of stone that separated the two halves of the passage. Dust still filled the air, and the mountain still pressed down with its silent weight. But something had changed. The granite ahead had begun to sound different. Engineers listening to the vibrations through the machine's frame noticed a hollow resonance in the rock. Each strike of the cutter head produced an echo that traveled farther than before. The granite barrier between the two tunnels had grown dangerously thin. Surveyors confirmed the measurement. Less than 10 meters remained. Work slowed deliberately. Engineers ordered shorter drilling cycles, allowing crews to inspect the rock wall between rotations of the cutter head. No one wanted a sudden breakthrough that might send unstable fragments crashing through the chamber. Finally, the machine advanced one final time. Steel teeth pressed against the granite surface and began to grind. The wall shuddered under the pressure. Hairline fractures appeared across the rock face, spreading outward like cracks in frozen glass. Dust spilled through the fissures as the cutter head rotated again. Then the mountain gave way. A section of granite collapsed inward with a dull roar, opening a jagged hole in the wall of stone. Through the cloud of dust came something that had not existed inside the tunnel for years. Fresh air rushed through the opening from the opposite side of the mountain, carrying with it the distant sound of voices echoing through the darkness. Workers on the southern drilling front had heard the final strikes of the machine and were already shouting through the newly opened passage. For the first time since construction began, the two halves of the tunnel were connected. Lanterns appeared in the opening as crews from the opposite side approached cautiously through the broken granite. When the dust finally settled, the workers stood face to face beneath the heart of the Alps, surrounded by the rock that had divided them for so long. Above them, thousands of meters of mountain remained. But the barrier had been pierced. The completed tunnel stretched for more than 15 kilometers beneath the granite peaks, forming the longest railway passage the Alps had ever known. Where caravans once struggled across narrow passes, trains would soon travel through the mountain in minutes. Steel rails would replace mule tracks. Steam locomotives would carry freight and passengers through the same stone that had resisted every crossing for centuries.